Hello, in our second class, let's change the story and look into the European papermaking. Paper was developed in China and spread to the Islamic world around the 8th century, but it was not until the 12th century that papermaking techniques was introduced to Europe because it monopolized paper techniques for 500 years in Islamic society. So it began around the 12th century. More than 1,000 years later, paper was developed in China. Paper making technique, which was transmitted from China to the Islamic world, is believed to have spread to Europe from two places, southern Spain and Italy. The Muslim people who occupied North Africa at the time had been conquering Spain's Iberian Peninsula since the 8th century, and paper-making technique was introduced to Játiva, Spain in 1150. Meanwhile, Muslims were occupying the island of Sicily in Italy at the same time, and through this, paper-making technique was also transmitted to Italy. The Islamic paper technique settled in Europe is inherited by the Europeans by the withdrawal of the Arabs. In the 12th century, when paper making began in Europe, the demand for paper was very small, but with the commercialization of letterpress printing in the mid-15th century, demand for paper surged. The paper making industry developed considerably, and paper manufacture industry spread throughout Europe over about 300 years. Though the propagated only raw material is believed to be made from discarded linen fabric, which was mainly used in Islamic countries. But later, they start to use rags, which mixed with cotton and linen in their own way. All the fabrics of linen and cotton at the time were hand-woven ones, and especially cotton was excellent raw material that contains rich cellulose, but chemicals and bleaching agent were not used, which contribute to the high durability of paper. So it is an ideal material for making paper from the current mindset. Another characteristic is that there has been a major change in the way of fiberization process. In the Islamic world, alkaline lime water was used to fiberize the discarded fabrics, but it was not used in Europe. Instead, a method of fermentation and decomposition of fibers was applied. This method first shreds the old fabrics and turn them into a netted container. Then foreign substances such as sand are removed by discharging them through the net. After that, it is moistened with water, handed into a bowl shape, compressed, and stacked. And in this state, it is maintained wet for 6 weeks to 2 months, fermented and decomposed. And then the temperature inside the fabrics rises, fermenting, and the color is unique like the color of the residual wine, like a pomace. However, in this process, about 1/3 of the total raw material decompose and disappear, so it was wasteful. Of course, in Europe in the 15th century, there were no various fabrics like today, but collecting discarded fabrics was not a very big deal at the time, so it was okay to be wasted. And the remaining 2/3 of the raw material is completed in a state of soft fibers suitable for papermaking. Then it becomes easier to conduct beating with the soft part. On the contrary, if you stop fermentation quickly, it becomes crude and hard paper. For your note, European rivers contain a lot of alkaline lime. The fermentation was promoted more easily. In this way, the lump of discarded fabric is fermented, and when there are signs of weak mold in the process, it can be judged that the process has progressed very well. Some factories apply lime directly to discarded fabrics to promote decomposition, but this only damages the raw material and does not have the same strength and durability as naturally fermented paper. However, in the 19th century, France began the process of forcibly decomposing raw materials using only lime to shorten the processing time. Anyway, after the fermentation process, the discarded fabric is cleaned. During the fermentation process, the fiber becomes dull yellow, and the reason why European paper is creamy like this is because this fermentation process has a great influence. Bleach began to be used in paper manufacturing in the late 18th century. But before that, because chemicals were not used, the paper made before that had a hue of raw materials, and as a result, the hue was significantly different depending on the quality of the paper. For example, high-quality paper is creamy, and crude paper made from old and faded raw material has a light coffee color or darker gray color. After fermentation of rag is completed, the raw material that has been decomposed and softened is washed to remove the contaminants and put it in this hole. This is called bath holes, which is made of stone blocks or oak wood, and this hole is covered with iron or reed plates in the bottom. And with the power of the water wheel, a hammer in the shape of a wooden pestle called a stamper moves up and down in the hole to tear the fiber. When paper making technique was first introduced in Europe, with regard to beating conducted in Europe, it is thought to have used manually moving mortar or millstone, just like those performed in the East Asian countries and Arab. But it wasn't long before a better way was devised, and in the city Sativa in Valencia, Spain, a water-powered stamping mill was devised around 1151. Looking at the structure of the stamping mill, it looks like an improvement to a mill that moves by water wheel. This is the device seen in France, consisting of a large row of wooden hammers moving up and down by such a strong rotating shaft. I will show you a short video of beating is conducted in France. Next, let me explain how to make the paper in Europe. The principle is quite similar to the way of East Asian countries, so let me explain briefly. The worker stands in front of the paper making bath and grips both sides of the square-framed metal screen, which is called decal, tightly. The bath is filled with the beaten fiber suspension. Then soak the decal almost vertically into the pulp suspension and lift it horizontally. With this operation, the screen is uniformly covered with a pulp suspension, so an extra pulp suspension unnecessary for the thickness of the paper is flowed out from the tip of the decal. And the worker gently shakes the pulp suspension on the decal from right to left at first and from back to front. By doing so, the orientation of the fiber hardly appears, as in the Tamezuki method introduced earlier. And at the same time, excess water is flowed down. Let me show you a short video of paper making. In this video, Mr. Jacques Breger, who is reading his papermaking studio in France, showed me making paper by only himself. But originally, 3 workers are cooperated to make a paper sheet. Batman makes a wet sheet using a metal screen. Then Kocher is take over the screen and pile up the wet sheets, and then paper bundle is pressed. And Rayman takes off each paper to dry. In such a way, paper is made and pressed, and then dried indoors by hanging it on a laundry floor. And other processes remain after this. There is still a process to prevent smudging, like ink sprayed or bleeding of paint. Originally, paper was developed for use as a writing material. However, since paper has the property of absorbing water, it penetrates into the capillary tube of the fiber and diffuses when moisture touches it. Therefore, when writing or printing letters with ink with a pen, it will spread. Therefore, in order to prevent moisture from entering the capillary tube of the fibers, the capillary tube should be blocked, or a flat film should be made to prevent moisture from entering the capillary tube and be treated to prevent it from smudging. This process is called sizing. And in this way, animal protein is extracted by peeling off the animal skin, processing, and boiling. The animal protein is identical to gelatin, which is once filtered and dried paper is immersed again in gelatin solution, and by compressing and drying the wet paper again, it prevents smudging on the paper surface. At the time, it was called tub sizing because gelatin solution was treated in a tub. Alternatively called gelatin sizing, which is the method used since the 14th century. However, the problem was that once the dried paper is wet, it should be pressed and dried again. That is annoying double task, and there was a lot of waste because the paper was torn or damaged during this process. So it was inefficient. Also, many books from the 15th century were printed on non-sized paper because sizing process was essential for writing letters but was not essential for typography, the letter print. Over time, the demand for paper increased rapidly. In the first half of the 19th century, when the Industrial Revolution came to an end in England, Europe's economy stabilized, but at the same time, demand for paper exploded. As a result, linen and cotton fibers that had been used up until then became insufficient for the supply of paper materials. Therefore, a method for obtaining pulp fibers by chemically treating wood has been developed. The paper we use on a daily basis now is basically wood pulp paper. Also, the sizing method has changed. Like conventional gelatin sizing, it takes a lot of time and effort to wet the paper once made again. So in 1807, a man named Moritz developed alum rosin sizing. As a substitute for animal glue, there is an oil-like natural resin secreted from pine trees, which is collected and refined. And an alum was used to settle the rosin in paper fibers, which is a very grateful method because mixing them in a pulp suspension to make paper contributes to the sizing. They didn't have to bother wetting dried paper and drying it again. This method is called alum rosin sizing. Unlike conventional tub sizing, or which is called gelatin sizing, the addition of alum enables efficient handling of pulp. But the problem was that this aluminum sulfate is very acidic. In other words, the fiber suspension itself is immersed in acidic water, so the paper that has been made up naturally becomes acidic. The point is, a chemical reaction of aluminum sulfate with paper leads to severe degradation. So far, we have seen the origin of acetic paper. As the Industrial Revolution progressed in the late 19th century, the demand for paper exploded, making it difficult to obtain longer fibers such as cotton and linen, which had been used as the main raw material for paper, and transitioning to shorter fibers such as wood fibers. At the same time, regarding the prevention of ink smudging, the transition was made from gelatin sizing to cheaper and more efficient alum rosin sizing, which say that paper made by using a large amount of alum became acidic. Based on this background, let's look at the degradation phenomenon of acetic paper. Considering modern library facilities, we have to deal with a large amount of paper objects. The most difficult problem in considering the use and preservation of book objects is the degradation of paper caused by acetic paper. In fact, while there are book objects that have hardly deteriorated over hundreds of years, many book objects published over the past 150 years have become vulnerable in just decades. An article of newspaper Yomiuri in February 1979 on the issue of acetic paper shows the situation at the time. The title was "Can't You Read It in the 21st Century? Tattered Collection of Books." American libraries are in constant danger. Millions of bookshelves are in tatters. The problem is poor paper and bookbinding of books published after 1850, and their lifespan is only 25 years. Moisture, light, and air pollution adversely affect books. Acid discolors the paper and turns the pages to tatters. In the US Library of Congress, one-third of its 18 million books, 6 million books are badly damaged and cannot be repaired if they are lent to the public. Half of the books at the New York Public Library and Harvard University are in danger. Books printed before 1850 used paper made of cotton or hemp fibers and parchment with animal skins. These kinds of papers are less susceptible to adverse environmental effects than acetic paper, which has spread rapidly over the past 100 years. Organizations such as the Library Resources Council and the American Library Association are calling for the introduction of new technologies to neutralize paper acid. The Library of Congress in the US boasts the largest collection of 18 million books, and about one-third of the books, about 6 million, have been severely acidic degraded and cannot be repaired if lent in that state. First of all, how should we define the phenomenon of degradation of paper? It is nature's providence that everything in the world extinct over time, which is a kind of chemical change that occurs in a matter. However, among the chemical changes in a material generally considered, there is a reversible change in which a chemical bond is formed and it collapses and rearranges. Let me give you an example. This is nitrogen tetroxide, which decomposes when conditions such as temperature and pressure are changed to produce 2-nitrogen dioxide. It turns red when the temperature is high, but returns to a colorless state when it gets cold. Therefore, depending on the conditions, it goes either way, and each time the color changes as a result of a chemical change. So this is reversible because the state change is not one way, but round trip. However, the process of object degradation basically shows irreversible changes and actually occurs very slowly. Irreversible change is one of the characteristics of object degradation. This is a model of cellulose molecules, which are the main components of paper. And countless things called glucose are connected as minimum units. And each glucose unit is connected to form a polymer called cellulose. Chemical changes in paper due to various factors break the cellulose chain, which means that the paper becomes physically brittle as it is cut, although the rate of changes can be controlled, but the broken molecules cannot stick together again and recover their physical chemical state. That's why it shows irreversible change. Therefore, the main cause of degradation of paper must be the breaking of cellulose chain. Looking at the structure of paper fibers, the assembly of cellulose molecules is called microfibril, which has a strong area called crystalline region where fibers are arranged in orderly, and a weak area called amorphous area where the arrangement of fiber is messy. Because there are many gaps in amorphous area. So, for example, oxygen, moisture, and acids coming from the outside. But first, it attacks this weak amorphous region randomly. Among the degradation factors, acid is the most important factor that remarkably promotes cellulose decomposition, and moisture, oxygen, or light is a factor derived from an external environment that promotes degradation. That's why acid derived from aluminum sulfate, which is used in aluminum rosin sizing in European paper manufacturing, attacked cellulose chains easily. We can imagine that if the cellulose molecule is cut off from the edge, damage will be small. But the actual attack on the cellulose molecule chain is cut off at random. So if it is cut off in the middle, its length will be halved at one time and physical strength of paper will decrease rapidly. Although there is no obvious change in properties in the early stages of paper degradation, chemical degradation persists little by little. As a result, most of the cellulose chains are cut and physical strength of the paper decreases or changes in physical properties such as discoloration occur. In order to intuitively see the process of cellulose decomposing due to degradation, acetic paper manufactured in the early 20th century was carried out accelerated aging under high temperature and high humidity conditions, and then ground with a mixer. As you can see here, the longer the aging period of acetic paper, the more it is cut into the cellulose chain by the acid, so it becomes close to powder. On the contrary, the less cut in the cellulose chain, that is, the more connected the glucose units that make up the cellulose molecules, the stronger the paper and more resistant to degradation. Therefore, it becomes an indicator of highly preserving paper and is generally expressed as a degree of polymerization. Polymerization is an important indicator of the quality and permanence of cellulose. In other words, the higher the degree of polymerization of cellulose molecules, the higher the strength of the paper, and the stronger the resistance to degradation, making it a paper with high permanence. Let's look at this table. As a characteristic of cellulose in non-wooden fibers, the degree of polymerization of cellulose is often higher than that of cellulose in wood pulp. In particular, cotton, linen, and lamy are high, and Kojo, Mitsumata, and Gampi have already caused a decrease in polymerization during the beating process. But it can be seen that the degree of polymerization is higher than that of wood pulp. The 1,500 years old documents remaining in Japan also consisted of Kojo, Gampi, or their mixture, and it is not coincidence that the excellent permanence of traditional Japanese paper based on Kojo, Gampi, or Mitsumata is attracting attention, but due to this higher degree of polymerization. The relatively low degree of polymerization of wood pulp is due to the collapse of the cellulose chain in the process of separating fibers from wood using mechanical action or chemicals. Let me explain the model of cellulose scission by paper degradation more detail. First of all, as I mentioned before, inside the microfibrillae here, where cellulose chains are gathered, there is a strong area called crystalline region where fibers are orderly arranged, and there is also a vulnerable area called non-crystalline region or amorphous area where the fibers are arranged disorderly. And they have many gaps, so oxygen, moisture, and acids from the outside can randomly attack this weak amorphous area. And let's see an example in this model of cellulose chain scission in amorphous area. First, in stage of A, cellulose chains are attacked by acids in 4 areas among 8 areas represented by red arrows. Assuming that whole cellulose strength is 100, if the cellulose chains are cut once, then the strength is reduced to 50. Next, in stage of B, the part represented by red arrows in degraded cellulose chains with a strength of 50 indicates additional cuts in the remaining healthy cellulose chains, which in turn will result in reduced strength parser. However, areas represented by black arrows are cut the side of the chains, and it does not reduce the strength because they were already cut, but it creates fragments of the small chains. And the stage of C in the highly degraded cellulose, where strength drops from 100 to 25, most of the chains are cut as indicated by black arrows, making small fragments, and the few healthy chains are cut, which slightly reduce the strength because they occur from the remaining chains connected to the crystalline area. When paper deteriorates, cellulose chain scissions occur more frequently even in cellulose chains that are already cut as shown in black arrows. In this case, there is no decrease in strength by the scission of chains. Instead, small fragments of cellulose are formed. When the chain is cut at the most end, the product will be a glucose. However, as the paper deteriorates further, most chain scission produces not only glucose but also separate small organic compounds. Their production is important in the process of degradation of paper, where these small molecules accumulate and further cause chemical reactions among themselves. And some of them produce acidic substances such as carboxylic acid like acetic acid and formic acid, and paper accumulates this carboxylic acid to become more acidic, and the process of promoting the decomposition of cellulose chains will be repeated. In the early stage of paper degradation, there is no change in properties. Even the chemical degradation is small, and consequently, the cellulose chains are decomposed and cause changes of physical strength and discoloration. When looking at the changes in the paper as the cellulose chain is cut as the paper deteriorates, the strength of the paper first decreases and the discoloration becomes remarkable. The strength of paper is expressed by the strength of the fiber itself, and the fibers tangled like a network and stuck in layers to form a number of binding areas. However, as I said before, when the paper deteriorates, all the cellulose chains in the connected amorphous region are finally cut. This means that the fibers themselves are weaker than the bonds between the fibers. And such a paper is fatal to permanence because they are easily destroyed with just a little force. Of course, discoloration also damages the appearance of the paper, but it can be partially recovered by washing it with water or bleaching it. However, as I said earlier, there is no treatment to restore the original strength of cellulose once degraded. However, for reference, there is a method called lining with a wheat starch phase as an adhesive diluted with water using thin but durable Japanese paper, which is a simple method of mounting by attaching a lining paper to the back of the deteriorated paper. Alternatively, there are several ways to fill in the missing part with Japanese paper close to the original paper artworks when it is already missing. This time, I will omit the specific preservation and restoration method, but I will briefly introduce it. There is also a method called tejukuroi, a hand mending, in which Japanese paper for repair is pasted according to the dimension of the missing parts, and it can be applied in both Japanese and Western paper artworks, and is carried out using highly durable Japanese paper. If the area of the missing part is large or there are many places, we can select the reef casting technique. This first fiber suspension liquid is poured on the missing part while suction is applied from the bottom of the paper. Then the fibers are collected in the missing part. By compensating such a missing part by using the same material, a visual sense of incongruity can be reduced, but physical homogeneity of the whole paper can be maintained, and breakage or damage to the small edge of the missing part can be prevented. As for the discoloration, first of all, old paper can recognize the state by the discolored appearance. In this way, it causes the overall yellowing of the paper. Besides, when exposed to moisture or light, this yellowing causes local stain. This is called foxing, which indicates dark spots. This situation can often be found in the case of book, which can be promoted by secretion caused by microbial activity of mold, or by oxidation of high concentration of metal ions used in ink, or metal ions contained in water used in paper manufacture. As a result, if the degradation progresses in this way, the decrease in the strength of the paper cannot be tolerated, and discoloration hinders the reading of drawings or text information, so the exhibition cannot be endured. Let's take a look at the degradation of Japanese paper. Fortunately, Japanese paper was traditionally made with high durability of bast fibers, and there are little substances that could promote degradation. So, unless it was eaten by insects or burned in a fire like happened in Todaichi Temple, it would remain forever. That's why they thought it would be good to put it on the shelf properly. Especially in Europe, Japanese paper or Korean paper is often used for the purpose of repair of cultural heritage, because they are made of kojo fiber with high durability and no chemicals added to it during process of the paper making. In other words, the same is true for objects of all cultural heritage, because the objects are related with the permanence. Paper with a longer fiber length is advantageous for durability. The kojo is more advantageous, and bamboo paper is very short and fine. This is advantage because the printability is very high, but strength is relatively low. However, the manufacturing method may affect the permanence. In the case of Japanese painting, a sizing mixed with animal glue and alum is applied first to the whole surface of painting paper as the base material of the painting to prevent the smudging of paint. In this case, concentration of alum is higher than used in Europe. If it is applied too much, it becomes acidic paper, as I said before. Let me show you an example of destruction of aged Japanese paper coated with alum and animal glue solution. In the past, even the artists do not apply sizing so much, but for the repair work after aging, This sizing was applied on the painting paper by conservators to prevent the paint layer from peeling off. So no matter how alkaline the Japanese paper was, it became acidified at some point, causing the same degradation as in Europe. The other factor that causes degradation of Japanese painting that I want to introduce is pigment, which contains transition metal ion. Especially pigment containing copper ion is used to express green or blue color. But metal ion promotes oxidation reaction of copper, which contribute to the degradation of painting paper. This phenomenon is called malachite burning. As shown in this figure, charcoal-like discoloration occurs as light burns at the part applied in malachite pigment on the front side of painting paper is recognized. And the influence on the back side is increased too, because copper ion is migrated into the back side, so that the preservation of the hanging scroll becomes a big problem. When the degradation progresses, the entire paint layer on the painting paper side changes color and darkens. As I mentioned before, discoloration and decrease in strength will proceed, and the cellulose chain that makes up the fiber will be decomposed, and the paper will probably be lost in the shape of the paint. In Western books, iron gall ink is used for writing. Similar to malachite burning, which contains iron, can also cause the oxidation of paper and disappear around the letters as if the text is burned. So what I want to say is, let's remove the clips and staples from your resumes, because the iron that are released promotes the oxidation of the paper, which might become paper cultural heritage in the future. In summary, the origin of acetic paper was changed from cotton and linen fiber to wood fiber until then as the Industrial Revolution progressed in the late 19th century. At the same time, it transitioned to cheap and efficient alum rosin sizing in relation to the prevention of ink smudging. Wood fibers have shorter fibers and are more vulnerable to degradation than hemp or cotton fibers. And by using alum, the paper becomes acidic. Acid in the paper causes chemical reactions such as acidic degradation and cuts the cellulose molecules chains. If the paper itself deteriorates chemically in this way, it will be worn out within 100 years. The problem of acetic paper was born like this, and in the late 19th century, the fear of acetic paper spread mainly in Europe and the United States. It was not until the 1960s that the acetic paper began to shift away from its production trajectory and turn it into neutral paper. Until the acetic paper problem occurred, a term preservation in the library at the time was used in almost the same meaning as binding and restoration. Alternatively, there were cases in which measures against temperature, humidity, and insect damage in the library were included in this category. The policy of preservation was to deal with damaged books individually and to protect them from bad environments and pests. These are, of course, still important ways to preserve paper objects. However, considering the maintenance of books facing acidic paper problems, this level of response is insufficient. First of all, considering the scale, the object to be dealt with is not individual object, but the entire library. Besides, the problem of acidic paper is not an individual library problem, but all books in all libraries in the country are on the verge of acidic degradation. It is said that a large amount of books have already deteriorated and are in a state of unavailability. How can we deal with this? And unless effective measures are taken, the chemical reaction that causes acidic paper continues, so acidic paper increases every year. Besides, most of the newly added books are also acidic paper. Decades later, these also become difficult to use. Moreover, deteriorated books cannot be saved by repairing it to the extent of binding and lining, and the chemical treatment technique was still in the development stage. Above all, a huge amount of budget is needed to come up with these measures. Even if there are funds, the conservators in charge are not sufficiently trained. Then what should we do? In the 20th century, a number of studies have been accumulated among paper-related scientists to improve the paper-making technique of highly durable paper in pursuit of the causes of degradation of paper. Based on this research, it was only in the 1960s that the orbit was transformed from the manufacture of acetic paper to the neutral paper. In the middle of the issue of acetic paper, William Burroughs, who was the conservator and scientist of the United States, played a big role in this change. In pursuit of the cause of paper degradation, an investigation was first launched to find out what happened to modern book papers and whether they are still happening. So let me introduce the result of a survey of physical strengths on 500 books published in the United States. Between 1900 and 1949, 500 books published in the United States were selected for 100 samples every 10 years, and each paper was tested for strength. Regarding the strength of paper, it was judged that two things were most important. One was tear strength and the other was folding strength. The tear strength is an evaluation of the resistance required to tear the paper, and the folding strength is an indicator of how many times the paper can withstand it without breaking when folded repeatedly. Looking at the graph of the experimental result, it is clear that the tear strength and folding strengths are rapidly decreasing every 10 years. And what is important is that the tear and folding strengths are decreasing almost in parallel with age. Therefore, since it was possible to evaluate the strength of the paper by selecting only one item between the tear and folding strengths, Barrow compared with the folding strengths and showed the following 5 stages of strength. And the life expectancy of the paper belonging to each stage was estimated. Regarding the level of strength, paper with a lower strength than newspaper was set to weak, based on 24 times the value of the folding strength of newspaper, which was generally the weakest and least durable at the time. And paper with a lower strength than this and the folding strength of less than 3 times was set to very weak. And sample having 24 to 75 times of folding strength was set to medium strength A. Sample having 75 to 200 times of folding strength was set to medium strength B. And sample having more than 200 times was set to very strong. Since the strength of paper made from discarded fabrics made in the 16th and 18th century represent between 300 and 4,000 times, sample having more than 200 times was said to be very strong. According to a table summarizing the percentage of 500 books published between 1900 and 1949 belonging to 5 levels of strength and its predicted lifespan, 88% of the samples among the total were weaker than newspapers published at the time of the survey. Only 1% of the samples were expected to have long-term durability, and only 3% of the samples were expected to have a lifespan of more than 50 years. In other words, only 3% of the books published in the first half of the 20th century can withstand use in the 21st century, belonging to medium strength B and very strong. Most of the others will no longer be available. As a report on the degradation of paper, Burroughs raised the issue of remarkable degradation of book paper made of acetic paper for the first time based on the empirical data. However, Burroughs' research was still limited. First of all, the target of the sample was limited to books published for 50 years from 1900 to 1949, and the analysis was mainly about the folding and tear strength tests. Therefore, the age of a sample to be investigated has been expanded by 100 years from the previous one. An analysis of book papers from 1800 to 1899 was carried out. As we haven't seen so far, the 100 years of the 19th century is an interesting period from a research point of view because it's a period where a lot of changes haven't taken place in relation to the quality of book. As for the samples, 50 samples were selected every 10 years. As a result, let's take a look at the result of the pH, identify the fiber, and how much logen was contained in the paper. First of all, when it comes to the fibers that make up paper, between 1800 and 1849, almost all of them are 100% of legs, which means paper made from fibers obtained from discarded fabrics. So it's a piece of paper that contains linen and cotton fiber. And from 1870 and 1879, paper mixed with legs and wood pulp took over the mainstream. And after 1880, paper made of discarded fabrics completely disappeared. Between 1850 and 1869, it can be seen as a period of change from leg paper to wood pulp paper, indicating that it is changing quite rapidly in a short period of time. Next, the length of the fiber consists of 3 stages: good, medium, and bad. And even in this case, it is clear that the fiber is changing from paper of long fiber to short fiber. This corresponds to the change from long fibers of cotton or linen to short fibers of wood pulp. And most of all, because the length of the fiber gets shorter, it's going to reflect the physical strength of the paper. However, even in the period of using only 100% of legs before 1850, the length of fibers tends to be gradually shortening. And in general, the fiber of linen is long and the cotton is short. Until then, linen was the main raw material and paper made of cotton mixed leg was used. But since the early 19th century, paper with cotton as the main raw material has appeared. So you can confirm that the proportion is gradually increasing in leg paper. Next, we will look at the effects of sizing agents. This graph shows the pH change of book papers over a wider period of time from 1500 to 1949. And since pH is an indicator of acidity, we can see how the acidity of the paper changes as the sizing agent changes. As you can see, pH in the vertical axis decreases with time. In the 16th century, when gelatin sizing was common, the pH of paper showed a slightly neutral or alkaline state from 6.2 to 8. However, in the 17th century, the pH dropped to 5.5 and then further decreased to 4.5 in the 19th century. This is the result that can be seen as the cause of the increase in use of alum. Let's look at this table again. From 1830, a paper using alum and logen instead of gelatin appears, and the transformation into alum logen sizing can be seen from 1840 to 1869. And it can be seen that from 1870 to 1879, the proportion of logen accounted for 94%, and almost only alum logen sizing was used on paper. In terms of pH during this period, acid is generated from paper by using alum in logen, so the pH is relatively high at around 5.5 in the 1820 to 1840, but it has declined again since then. As for this sudden increase in pH, this graph corresponds to the protruding part here, and it is thought that the influence of a scientist named John Murray, who raised the issue of acidity at the time, was reflected in this period and temporarily reduced the amount of alum used. However, after the 1860s, it fell back below pH 5 and even strong acidity of pH 4.5 appeared. This change can be explained by the complete prevalence of large atom size. Let's take a look at how the physical strength of paper changes as pH gradually decreases and acidification progresses. The horizontal axis is the publication date, and the vertical axis is an indicator of the paper strength, indicating the number of porting. Looking at the graph, except for the details, the porting strength remains almost constant until the mid to late 17th century, but after 1670, the strength has certainly declined. As a new beating machine called Hollander beater began to be used instead of a stamping mill from this period, the fiber became shorter with beating, and the amount of alum used increased, though the forging strength was greatly reduced due to acidic degradation. Then, in 1774, chlorine was introduced as a bleaching agent for pulp, which acts strongly on fibers as an oxidizing agent and may also reflect damage to fibers. Influenced by these factors, the forging strength began to decrease significantly, especially after 1860s. By the way, the increase in forging strength in the 1820-1830 corresponds to what we saw in the pH graph earlier, and it's been falling sharply since the 1860s. This also shows that the strength of the paper is decreasing in response to the change in pH earlier, and especially after 1880s. This shows disastrous results. In the case of this level of forging strength, you can think that the paper is destroyed just by turning the page normally. As a result, most of rag papers maintain a high degree of forging strength and then reduce as they transition to wood pulp paper. Because the effect of acid as the amount of alum used increased also worked upward. So it was discovered that the lifespan of book was less than 100 years and it failed to function. So that's all for today. Thank you for listening.